system and look for errors at this particular, at so early a stage, then this is beneficial for my whole process. Because if I find out an error, a design error or a requirement error at a later stage, then I either have to roll back my code or say I have to make changes to the existing code, which is disastrous. Okay, so designing models at an early stage and analyzing them to find errors is a very desirable activity that actually people follow extensively. So for this purpose, there are a lot of conceptual models which are available. So you might have heard of UML models or class diagrams, or there are different state machines, or there are different logic available, or the algebras. So Alloy is one such design tool. So it's a combination of two things basically. First one is the specification language for describing structures. So this is the language in which you express your models. You say, these are my entities, this is the relationship between the two. So that is what the specification language does. But that's not enough, right? You express and then what? Do you frame it or something? No, you analyze it. You look at it and see whether it's satisfying everything you want, or is it giving errors, or it's not enough. So then Alloy gives you an automated analysis tool to explore the structures which arise out of the model. So a model is abstract. So you would have many structures arising out of a model. So it gives you a way to analyze those models. So combining these two, you get what is a design tool. Now, what exactly comes in specification language? So obviously I mentioned that specification language have entities and relationships between them. For example, UML model have these graphical structures. So Alloy uses set theory and relations to model these kind of relationships. Then you have certain constraints on your system. Say, let's say a student cannot be in more than one class. How do you express that? To express that, it provides you with logic. So it uses first order logic to express those things. Then you have automated analysis for the exploration of structures. So using those explorations, you could answer questions like whether your system is under constrained, right? Whether you are allowing erroneous behaviors, or your system is too constrained, you are not letting it move anywhere, you're not allowing the possibility of anything happening. So using these two together, what it allows you to do is either you can generate counterexamples that look, here is a counterexample which says that this system is not behaving correctly. Or you could explore the models and look for something that you might have missed while specifying things. Okay. Or the third thing it promotes actually is the modular refining of things. So we'll talk about modular refining when we look at the demo, but for the purpose of the tool, this is what it broadly allows you to do. So some preliminaries. Okay, so first of all a question, how many of you are comfortable or familiar with set theory, relations and logic? Almost all of you, right? So I'll go very quickly with the preliminaries, it's just that I need to brush them up. Okay, so as I said, Alloy has logic, it has a specification language, and it has what is called a bounded exhaustive search. Logic has two subcomponents called sets and relations and first order logic. Specification language is the Alloy language in which you express your models. And then you have the bounded exhaustive search which uses SAT solving. We will first discuss the first two components together because basically this is a notation for this, Alloy notation for this particular theory, and we'll discuss SAT solving later when we'll talk about how the tool exactly works. Okay, so first of all, sets. Very basically, set is a well-defined collection of distinct objects. That is it. It needs to be well-defined. The set of real numbers, set of integers needs to be well-defined because we need to check whether something belongs in a set or not. It's a true or false answer. And distinct objects, you cannot repeat it. You cannot repeat A multiple times in, say, a set of alphabets. So these are the only constraints on a set. So we've taken for the purpose of illustration two sets A and B. A has A1, A2 and B has B1, A2, two elements. So now there are different, as you might know, different operations which can be done on sets. First one being union, which merges the contents of two sets. Then being intersection, which gives you another set which contains the elements common in both the sets. Then you have difference, all the elements which are present in A and not present in B, which in this case is A1. So it gives you that set in the end. So the first three give you sets. Then we come to the subset operation, which checks whether a set is a subset of another set. So let's say we have a singleton set which has only A1 as its element, and whether its A1 is a subset of A, which is true because A1 belongs to A. Then equality, whether two sets are equal. They're equal if although all their elements are equal, which is in this case is not true because they differ in two elements, A1 and B1. Then you have what is called a product construction. Product construction or Cartesian product, what it does let's say if I'm doing A to B, then it gives me a set of pairs where the first element is from A and the second element is from B. It gives me all those sets. So for all the elements of A and all the elements of B, it gives me this set. So this is called the product construction. And these pairs are ordered. You cannot have B1, A1. These are always A1, B1. So that is the product construction. Before moving forward, any doubts? Yeah.
Inequality would be also like the count of elements, but just the element.
So the count of element would not matter because of this. You would not have repeated elements. So if I have ABC here, I will have ABC there. So they have to be equal. Right? Okay. Then we come to relations. So a relation from a set A to B is a subset of the product of those sets. That is it. Anything which is a subset can be a relation from A to B. So for the sets we took as example, let's say I define two relations, two arbitrary relations. One is R1, which has these two pairs, and the other one is R2, which has only this pair. So these are all examples of relations. You can construct many such examples. Now there are certain operations which are allowed on relations as well. The first, first of all, let's say to visualize a relation, you look at it as a table. So there are different ways of visualizing it. You can visualize it as a graph, but here I am taking a table. So the table, the first column is the first set, the second column is the second set. This is the relation R1. Right? Now looking at this, we have two concepts, which are called arity and size. Size is the total number of elements in a relation, which is 2 here and 1 here. Because it only has one pair and this has two pairs. Second one is arity. Arity is the dimension of the domain. So domain is this, A cross B for R1. Now it has two sets here, so the arity becomes 2. It could have had 3 sets, 4 sets, so then it would become a binary. So with arity 2, it's a binary relation. With arity 3, it's a ternary relation. And so on. So these are some terminologies related to relations. Now, the first operation that we're going to talk about is relational join, which is expressed as R1 dot R2. So these operators that I'm using here are actually alloy notation for those operators. The mathematical notations differ. So this is the relational join. Don't look at the answer right away. So I have R1 here and R2 here, expressed as tables. What relational join does exactly is, for the second column here, that is for the last column here and the first column here, wherever the values match, it gives me a set which is the rest of the values here and the rest of the values here. So it gives me A2 and B1. For the places where it does not match, it just simply discards those. So that is called a relational join. It's similar to a join in databases if you want an analogy, but yeah, that is what a join is. Based on the common values from the last column here and the first column here, you merge the entries and drop the common ones. So that is your relational join. So that is the answer for R1 dot R2. Then we have transpose. Transpose is expressed as tilde R1, which what it does is say R1 is this relation, the transpose of R1 is the flip of that. B comes first and A comes later. And you just flip the order of each of the pairs in that. So any question about these two operations? Join, is it? Okay, so you have these tables, right? Visualize these as tables. So you have these values here. So you want to join them according to the relation. So A is related to B. B is related to something else. You want A and C to be related, right? So what you do here is, you see what is this last value here, and you see what the first value is here. And then you simply join the data here to the data there. So what you get in the end is the columns here and the columns there. You drop drop the common one. So the answer would be A2B1, which is here. It's a new relation. It will give you a set of ordered pairs, which are constructed this way. Right? Clear, or do I explain again? Okay.
Actually, I'm not getting how we got the rule.
How you got
The
the?
output got one row, right? A to B1.
Yeah.
Yeah. You eliminated what from this?
Okay. So I have two rows here, A1, B1, A2, B2, which are the pairs in relation R1. Then I have R2, which is A2, B1. I have a single row there. Okay. Now I need to take a join of those, relational join. What I'll do is, so I'll see the last column here. I'll see the first column here. Okay, wherever the values are matching. So in this case, only this value matches. Okay, so there are entries corresponding to this value in this relation to the left. There are entries corresponding to this value in this relation to the right. Okay, I take the values to the left, join the value towards the right. For every pair I do that. This is my relational join. And I don't keep the value which was used to equate. That is your join. Okay. Then we have something called a transitive closure and a reflexive transitive closure. These are important operations which would be required in alloy, so that's why I'm discussing here. So let's say I have a set called C. Let's say I have a set called C which has elements C1, C2, C3, C4. Now are you guys aware of the property reflexivity? When everything is related to itself, right? So identity is a relation in which every element is related to itself. So this is a constant provided in alloy. So it would vary with different programs, but it's a constant. For a given program, it's a constant. So we use this for these two relations. So what is transitive closure? So let's say I have this relation R here, which has these pairs, C1, C2, C2, C3, C3, C4. That is C1 is related to C2, C2 is related to C3. Okay, what transitivity says is if C1 is related to C2 and C2 is related to C3, then C1 is related to C3. And you go on adding such pairs, until you can add no more pairs. So this is called the transitive closure. The reflexive transitive closure also includes this set for a given set. Okay, so these are the four operations for relations. Any doubt in these two? Yeah. Which one? Transitive closure. So transitivity is a property, okay, which says, say C1 is related to C2 and C2 is related to C3, then C1 is related to C3. So if I'm okay, so C1 is related to C2, C2 is related to C3, therefore we add the pair C1, C3 into the result. That is a closure. Because we added C1, C3 and we have C3, C4, we added C1, C4 in the pair, in the set. So that is how you proceed until you can add no more pairs. My time. Okay. Yeah, so any doubts here? Okay, we proceed. So now we come to how alloy declares sets and relations. So this is the keyword. Sig is the keyword which stands for signature, which says that this is a signature for a set or a relation. A is the name of a set. Okay, so A is the name of a set, F is the name of the relation, and EXPR is, we'll talk about EXPR in a while. So F is the name of a relation, A is the name of a set on the, F is the name of a relation on the set A. So F would be of the form A cross and something else. What that something else would be defined by EXPR here. Okay, so for example, if we have, so here EXPR, first of all, it could be of the form N range. Range is the range of your relation. That is the second component. So we had A cross B, so B is the range. And N is the cardinality. So cardinality decides how many elements of B will be related to any element in A. So if I say 1, then only one element of B could be related to an element of A. If I say lone, then 0 or 1 elements of B could be related to one element. Sum means at least one should be related, and set means it could be related to a set of elements. Okay, so to take an example, let's say I have a set called student. Now students can have belongs to a class, right? So a student can belong only to one class. So this is a relation class which has a cardinality 1. I say a student belongs to one class. Similarly, if a student takes courses, then it could take a set of courses. So that is how I define the relation courses. Now, alloy allows you to have relations with greater arity than 2. So the second grammar actually gives you how to declare, say, relations with greater rarity, and we're not going into that, but you can look up the technical specifications if you're really interested. Okay, then we come to logic. So logic has two values, true and false. You have propositional logic, in which you have a statement which could either be true or false. Something like sun rises in the east, which is true. So the main condition is it should have a logical value. That is it. Then you have operators over it. So you have or, and, not implies if and only if. Or means, so P is called a proposition. So P or Q is true whenever either P is true or Q is true. In other words, P or Q is false only if when both P and Q are false. P and Q is true when both P and Q are true. Not of P is true when P is false. That is, you flip the value, logical value of P. Implies means, implies is false only when P is true and Q is false. I'll show the truth tables for that, just bear with me for a while. Then if and only if is true only when both P and Q are true or both P and Q are false, otherwise it's false. So that brings us to satisfiability. So what we do in logic is because we have only two values that a variable can take, so we construct these tables. So as to for what value of P and Q, what is the result? So this is the table for P and Q. We can see that it's true only when both are true. Similarly, a table for or, for implies. And this is a table for the formula P and not of P. Okay. So the concept of satisfiability is a formula satisfiable if it is true at least once. What I mean by at least once is in this table. It is true at least once. Okay. So clearly this is not satisfiable. The more important concept is of a satisfying assignment. Satisfying assignment is an assignment which makes a formula true. Okay. So in this case, all the bold marked, red marked assignments make a formula true. This would be useful when we'll discuss about how alloy works, but just keep this in mind for some time. So alloy uses what is called first order logic, which is strictly more expressive than propositional logic. It's very convenient. So it allows us to express logical properties about collections of objects. Okay. So let's say I have to express something like every man is mortal. Now if I use propositional logic, I'll have to say something like man 1 is mortal, man 2 is mortal, and so on. Okay. I have to enumerate every man possible. But in first order logic, I could just say for all m such that m is a man, implies m is mortal. That is how you iterate over things. That is how you express properties over collections of things. So are we on the same page so far? Okay. So I'll just talk about what are the different components of first order logic and proceed. So this is called a quantifier. This is called for all. That is for all possible values of m. There is another quantifier called there exists, which says at least one value, such a value exists. So these are the two kinds of quantifiers it has. Then you have m, which is a variable. Man, here it's a predicate. This is a predicate. Then this is a connective, logical connective. These are called atomic sentences. This is a sentence which connects two atomic sentences using a connective. And this is a whole sentence which is connected using a quantifier. So these are the different terms in first order logic. So there are different quantifiers which alloy provides you. First two being all and some, which is for all and there exists. Then you have three additional quantifiers which say no. That is, the condition holds for no such thing. Right? Lone means it holds for at most one. And one means it holds for exactly one. So it provides you all these kinds of quantifiers. And so the way to express this is like this. For all x belonging to E, or for all x belonging to E1, Y. So these are the different ways you can write an alloy. So let's take an example and say all students are assigned to a class. So how would you express that in alloy? That is how you will express. So you will say all S belonging to student and 1 C, that it holds for only one class, that S dot class equals to C. That is, every student has only one class. Similarly, can you tell me what you need to say for all students have at least one course?
All students some
Hmm.
course
Then
course of work
S dot course.
equal to C course.
S dot course equal to C.
For all students, there exists a course
Huh.
that student is assigned to that.
How do you express? So S dot class is actually gives you the class of the student, right? Yeah.
For all, all S students,
Hmm.
there exists a course. How do you write there exists?
There exists is this sum. Hmm.
Some C class
Some C class.
such that S dot class
S dot class is C.
equal to C.
It's not equal to C. It would be subset of C. So C is a subset of S dot courses because course is a set. C is a single element. Right. So it would be a subset. Okay. So that is for about quantifiers. Any doubts so far? Okay. So just before proceeding, everything is a relation in alloy. So you can express singleton, you can express values as singleton sets, and you can express sets as unary relations. So alloy models everything as relations. So this is okay. So now we come to the tool demo, but before that we'll first talk about the example which we are going to take. So this is an example I took from Dr. Raghavan's class, every bit of it. So so this is a genealogy example which traces lines of descent. So you have people, men and women, and you have relationships which are father, mother, spouse, and you see what are the ancestors, which is a grandparent, etc. And you have to put all those constraints that a person cannot be both a parent and a spouse to a person, and things like that. So we proceed. Just a minute. Okay. So this is what alloy looks like. So why is it not showing? Why is it? Just a minute, I'll have to close this, is it? Okay. Is it visible to everybody right at the back? Yeah? Okay. So this is what an alloy file looks like. So it is divided into two parts. One is the signature part, right? The other one is the facts part. So signature declares all your sets, all your relations. Facts are the constraints that you impose on your system. Okay. So first of all, because it's a genealogy, we need people. So first of all, we declare people. Now every person has a relationship with at least one person, at most one person, sorry, the spouse relation. And then it has a set of parents. You cannot say it has two parents. You will have to say they have a set of parents. We'll constrain it later. Now you declare man and woman. Now man and woman are people, right? So this is a relationship you say that it extends person. Now you put this keyword here, abstract, which means that whatever subsets you've declared of this particular set using extends is actually covers this particular set. So there are no people which are not men or women. So it's a kind of a limited society. So you can't have other people. So so that is basically your signature. And then you have parenthood and social norms. So first of all, parenthood. So every person should have a woman as mother and a man as father. This is the formula which expresses that fact. Then you have some social norms, right? So first of all, spouse is symmetric. My wife, I should be the husband of my wife, right? No. So that is what it says. Symmetric. This is the transitive. This is the transpose. So this is how you express the symmetry. Then a man's spouse is a woman and a woman's spouse is a man. No same-sex marriages allowed yet. Okay. Then you can't marry a sibling. No Game of Thrones. Then you can't marry a parent, which is messed up. So then your parents should be married. Well, you can't be divorced. So this is a very not so modern society. Okay, so this is our specification. This is our model of our genealogy thing. So now you look at it, you just look at it. Assume that these are the requirements you got from a client. This is how you documented it. Can you see something wrong with this? Can you find an error just by looking at it? This is pure math. Nothing could be clearer than this. Can you find an error? No, you can't, right? You can't look at it and see how things might work out. So this is where Alloy is really helpful. What I'll do is, I'll generate instances of this model and we'll study those models and see whether we can find something off there or not. Okay. So this is an empty instance, which is always possible. So now we have this. So you have these different relationships here. You have the parent relationship marked in red and the spouse relationship marked in brown. Zoom. How do I magnify this? How do you magnify? Yeah. This is a useless zoom. I can't zoom, but okay. Okay, so are you able to differentiate between the red ones and the brown ones? No, right? So I'll show you the brown ones first. These are the spouse relationships. So you see, man 1 and woman 2 are married, man 0, and so I think everything is okay here. Let's see the parents' relationship. So the relationship means woman 2 is the parent of woman 1. The head means the parent. Okay, now look at this relation and see if you can find something which is not right. Man 1 and woman 2 have single parents, but that is okay. Woman? Yeah, you have these bidirectional arrows saying I'm parent of my parent, which is not right. Okay, so we obviously need to fix this. So this is what I meant by modular refinement. Okay, you built a system, you saw that there's some problem, then you add constraints to it and see whether it works or not. So next we come to, so what do we need to add here?
The instance that you were generating, was it generated automatically or you fed this instance and then tried to find out whether there's something wrong with it?
No, what I fed was this set of formula which I've given to the system. The system solved it based on these constraints and these sets and generated an instance which satisfies this. It's correct. As per your formula, it's correct. But in real world, is it or is it not? That is for you to decide. That is it. So it's all mathematical solutions to a problem. So what do we need to add here? By the way, what constraints should be added here? P dot parent, that is, if I can generalize it, you cannot be your own ancestor, right? That's a fair addition. Okay, so now I've added that. So no person is their own ancestor. This is how I add it. So no person, P in the transitive closure of parents, right? This is how you say parent, my parent, then their parent. So this is the transitive closure of that relationship. Okay. So you said that you should not be your own ancestor. Now let's see what instances it generates. We found an instance, and this is the empty instance which satisfies all these formula, and that is it. Your system does not generate any more instances. You have over-constrained your system. So you specified something which made it too restrictive that nothing can happen in your system. So what did we miss? Which is true, we need that. But because of that, what minute detail we missed?
Every person has a parent. This will create like person should be at the top of the.
So we need somebody to be at the top, right? Let's call them Adam and Eve. So Adam and Eve cannot have parents. They are the first man and woman. So we'll need Adam and Eve and say that except for Adam and Eve, everybody has a parent. Okay. So that is what is specified here. What we did was we say, for all P person, which are not Adam and Eve, everybody has one mother and one father. Okay. And we say that Eve is a woman, Adam is a man, and both of them are singletons by saying one before the signature. That is how you can actually talk about the cardinality of different sets also. So the lone one sum here are the same as the ones here. Okay. So we've done this. It looks fine now. Now let's see what instances are generated. Acha, looking at this, can you still figure out, did we do something wrong? Are we still missing something? Yeah, because of the rule, you can't marry a sibling, right? So that is what it's going to generate. I'll just show. So all the models here stop at generation 1, right? To fix this, what do we do? How? Huh? But okay, that is one solution. What I would do is I would allow the children of Adam and Eve to marry. Okay. So this is what the next step would have, what I would do next. So I've changed this rule, can't marry a sibling. If Adam is in the parents, you're allowed to marry. Okay. So now if you generate instances, you get, say, at least a series of generations. So this is how alloy works. Now if you see, there's a command called run show for 7. This is the limitation of alloy. So it's not exploring all possible values, all numbers of people, say 10, 20. You are giving it a bound. You're saying evaluate this particular formula for 7 people. Evaluate this particular formula for 2 people. So what the guarantee alloy gives it, till 7 people, everything is correct. After 7, there are no guarantees. So if you find no errors in this model, there's no guarantee that there won't be any errors after that. So you would still have to check it. So that is the limitation of alloy. This is called the bounded exhaustive search. So it's bounded, it's exhaustive. So that is what you mean by the search. So, okay, I have 10 minutes, right? I thought of giving a bonus demo, but never mind. So alloy is very interesting. Actually, you can solve puzzles and everything. You can all codify it and it would give you solutions. So it's very interesting just for the sake of fun. So you can go ahead and look at it. So I just want to go very quickly over this. How does alloy work? Okay. So the alloy architecture is as follows. You have alloy facts and signatures, the set declarations and the constraints. You give it to the alloy translator. It converts it into a first order formula. Then it gives it to a solver. The solver gives you a bunch of solutions. Then you have a predicate at the end, which we did not use. Our predicate was empty there, but you could have predicate later. The predicate would check these solutions, and whichever ones pass are given as the final instances. That is how broadly alloy works. So yeah, that is what it will give in the end. The problem is here. How do we make it so? Solving first order formulas is undecidable. Okay, and you would need manual assistance to have proofs or to even say whether it's satisfiable or not. Second, also if at all there was something that could do this, you still won't have multiple instances of those. So which are the two very desirable desirable requirements for alloy. So we need something else. This is doing something else. It's not solving FO formulas. It's doing something else. What it's doing is converting it into a propositional formula. So let's say we had this. How does it convert it? So we had this. We had person, man, woman, and let's talk about this particular constraint: man dot spouse and woman. Okay. So I say run it for 2 people. So what it does, it generates Boolean variables. So because it can have 2 people, it can have either 2 men, 2 women, 1 man, 1 woman. Okay. So I generate variables for all of them. So if there are 2 men, M0 and M1, 2 women, W0, W1, and then I instantiate all the relations also. So S00 means person 0 is married to person 0. Okay? Person 1 is married to person 0. Things like that. So that's how the spouse relation goes. Besides this, because okay, what does it mean to have this Boolean variable? So if M0 is true, it means that it belongs in the final solution. So, okay. Besides this, it generates certain constraints from signatures. Now remember we said abstract person, abstract sig person. And man and woman actually are, first of all, they cover it completely and are disjoint. Okay. So if man 0 exists, then woman 0 cannot exist. If woman 0 exists, man 0 cannot exist. Similarly for woman 1 and man 1. So this is a constant, this is XOR operation, okay, which says exactly what I just said right now, and it should hold for the whole formula. Next what it does it, so M0 M1 is actually a vector M0 N1. Spouse is actually a matrix like this. Now man dot spouse is nothing but matrix multiplication. What it does is, it constructs this formula, M0 S0, so M0 and S0, and is multiplication or is addition. So M0 and S0, M0, M1 and S1 and OR them. So this is what you get for man dot spouse. Now what you want to check whether is in woman or not. So what it means is, so now would you express, the way you would express it is this. So if this is true, this implies that woman 0 exists. If this is true, then this implies that woman 1 exists. You can read it as, if M0 exists and M0 is married to some person 0, then it should be woman 0. Similarly, if M1 exists and M1 is married to person 0, then person 0 should be woman 0. Now, this is an erroneous case, but this would be ruled out by this. Right? M0 can't be married to W0. So this is how you would convert a first order formula into a propositional formula just because you have initially given a bound. And SAT solving, though NP complete, we have very efficient SAT solvers, which Alloy uses. So this is the whole working behind Alloy. So the final solution would be this combined formula. And so what could be the possible instances of this formula? So you could have either 2 men, or you could have 2 women. You could have 1 man, 1 woman, but not married. You could have 1 man, 1 woman, but married. These are valid instances, and these are what you wanted. So that is Alloy. So to summarize, so we know that design is a key activity, and it's good to discover errors early. It's good to design your system first. And so Alloy is one tool for which you can use. So Alloy has been used for numerous activities: protocol design, hardware design in terms of cancer machines and all. Software design, there are a huge bunch of papers which only talk about the formal methods usage and how to model requirements or how to design a system. So it's not a very trivial tool. It's a very not a trivial tool and not a very trivial concept as well. So it's a design tool which lets you specify the design and also checks it. You don't have to construct it and see for yourself. The manual part is very less, and then it uses all these relational calculus for specification and SAT solving for analyzing the models, and also provides a very user-friendly UI to explore all the models, which is very convenient. That is all. Any questions? Well, thank you.